Okay. Hi everyone, I'm Matteo Schulz, first year PhD student at Gran Sasso Science Institute in Italy, and today I want to talk and take you through my current work, which is cosmology with gravitational wave and hydrogen cross-correlation for future observatories. But let's try to start slow. Let's have like a more insight by the title. Because the main idea is actually to trace large-scale structure with angular cross-correlation by using two different tracers of this scale structure, which is, as said, gravitational waves and neutral hydrogen lines in the use of cosmology. So let's, again, start very slow. What is large-scale structure? I guess most of the people in the room knows. Is, as the name says, a very large structure which spans all over the cosmic space and history, and actually is linked to the fact that there is matter clustering around due to some cosmological laws which are within our universe. So the basic idea is that if we are able to kind of trace this kind of structure, we could eventually, by pinpointing how it's formed and evolves, actually pinpoint and fix and find some cosmological constraints based on this. On the left, by the way, you can see actually the observation did by GWxHI, and also on the right you can see the simulation by the Illustrious project. But let's go ahead and try to explain to you what's the basic approach that in this kind of it's used. So I just skim through the basic idea, and then we can talk about how to go further in this. So first is that, as I was pointing out, we have the same underlying dark matter distribution, and we want to use different traces of this underlying distribution, and we use, therefore, gravitational waves. And in the basic approach, we use galaxy surveys, as all know, actually also trace the structure and the matter in the universe. So, however, the main point is that galaxy surveys actually have this kind of clustering statistics in the redshift space, while we have that gravitational waves have the clustering statistic in distance space, in luminosity distance space. So if we want to use some kind of connection to find some correlation, actually by using this multi-tracer approach, we are able actually to unlock the cosmological information we are looking for. So how to do so? The point is to, as said, access properties of two different traces of the same underlying density field with two different spaces. And by exactly combining this, or by trying to combine this data, the point is we want to find some connection, some relation between the redshift and the luminosity distance. And the cross-correlation, so by combining and correlating these two different maps, we are able actually to find this correct relation, because cross-correlation will eventually pinpoint, maximize out when we have or we find the correct distance redshift relation. So once we fix this relation, we can actually then evolve and constrain actually cosmological parameters, because we have fixed the distance redshift luminosity distance relation. So, but as you remember from the title, I was not speaking about galaxies, or I didn't want to speak about galaxy surveys, but do a step forward by using actually neutral hydrogen, in particular neutral hydrogen intensity mappings, as a new traces. Because as you also may know, also neutral hydrogen is the most abundant element in the universe, so it's actually fitted actually to do this kind of similar approach in actually trying to understand the cosmos. So why hydrogen? First and foremost, we have that hydrogen, as being the most abundant element, actually covers a very large, and it's always everywhere in the universe. So we actually are able to cover very fast big volumes of the universe, because despite, in the case of galaxy catalogs, we are actually need to resolve each galaxy, while in the neutral hydrogen case, we can also just use like the diffuse emission. So we don't need to fix and like really resolve each galaxy. And the second point is actually also hydrogen has the fact that we are looking for lines. So we have very high precision in redshift distribution, and at the same time, we get also high precision in matter abundance, because we actually, through the observation of the lines of hydrogen, we're actually able to measure the amount of matter which is in each line. And while on a last reason, let's say more practical, is that we are also willing to look for synergies between upcoming telescopes and observatories, mainly from a gravitational wave side, Einstein Telescope, while on the hydrogen radio side, we are looking for synergies within the Square Kilometer Array Observatory. So this as a start, let's try to dive through and into this topic. Just to give you a brief idea what we are speaking about, we are looking for trying to look for this quantity, which is the angular power spectra, because this kind of quantity includes automatically, or like within its definition, the effects of large scales. In particular, what is this spectra is just, let's say, a spherical harmonic projection of the matter density of the field. So in a certain sense, we're just projecting the fluctuations of the matter field on top of a spherical harmonic. So let's say you can imagine to look for some maps like the full sky maps. So this said, we can start to build our simulation by actually start building from the very top, from the very bottom, sorry. And so by actually trying to use, or like by using this class, which is a public available code for cosmology, which enables us to build and simulate the underlying dark matter distribution. In particular, we are able to produce these plots, which are, as I was pointing out, the spectra for this angular power spectra for different monopoles, which are representing in a certain sense the angular scales at which we are looking for correlation between the maps. So you can see we do this actually at different redshift ranges, because we are actually also looking or interested in looking at the evolution of the spectra, so to get eventually also an information about the evolution of the universe. So once this is done, we had to do first a small cross-check, because as you might know, we are also, like this code uses just linear theory. So we are there for perturbation evolution, while we might have some nonlinear effects happening at some scales. So to do that, we used some n-body simulations, which naturally include any or like most of the second order or like nonlinear effects, and we try to compare the spectra given by the two methods. You have on the black solid line represents actually the spectra you have just shown in the previous slide, so the dark matter one computed with the code, the class code, while you see the blue solid line is the one computed by through the n-body simulation. So you can see that in most scales there is not actually any differences, or like small, which is not actually any solid reason to change to a more computatively expensive method by using n-body simulation. So the only thing you can notice eventually here in the very bottom right corner of the slide, of the plot, there is some deviation happening. But however, in our simulation, with the upcoming telescopes, we will not be able to detect or like to resolve such small scales in angular scales. So we are actually just sticking on the left side of the dashed gray line, and so we are actually in this regime in which we are fine to use linear theory. So this said, we can start, once the dark matter distribution underlying is fine, we can start building on top of it. So we have to take into account of different contribution of the two different maps, especially gravitational waves and hydrogen, in which we take into account these biases, which are just some expression to take into account all the different effects given by the evolution of these two different traces with respect to the underlying distribution. And once we can also take into account about the redshift distribution of the traces. So you can see in the plot, the histogram is actually the distribution of the number density of gravitational waves, or in particular, when I talk about gravitational wave, I'm mainly referring to binary black hole events. And while the blue lines are actually ones for hydrogen. So by taking all this into account, we can actually build our maps. So again, these are just simulation. In this plot, we have on the top the one for hydrogen, which at very low redshift, as you can see, while on the bottom you see the corresponding one for gravitational waves events. So you can see this takes everything into account, and however, I was saying, are not just interested in a very local redshift bin, but we actually repeated a simulation for all the redshift bin, or like up to redshift 5, which is more or less the redshift range at which we assume there is some kind of synergy between gravitational wave, or like ET, for example, and SKAO. So once all these maps are done, we could actually start to do actually the proper work. So trying to combine all these different maps to try to find some spectra. There are different possibilities to how to combine these spectra. We have on the left the autocorrelation, which on this side, which, what does it mean? It means actually that we are taking, for example, the same map twice. For example, sorry, for example, we take this map twice, and we do correlation between these two maps, and in a certain sense, we get the variance of the map or like the matter fluctuation. In which, on the left, you can see, and the blue line represents the hydrogen map, and the variance of the hydrogen map, while the red one represents the gravitational wave ones. The other possibilities are actually to do cross-correlation. So we have two possibilities for cross-correlation. Either we take, for example, the same map, for example, for the same tracer at different redshift. For example, we can look for correlation between these maps and the following one. Or either we can also take correlation between the same different tracers but same redshift. So for example, take this map for a hydrogen and the corresponding one for gravitational waves. And this is actually what you can see on the plot on the right. You see that we are combining at the same redshift bin, we combine gravitational wave and hydrogen. So all this is set, so we can start to analyze this kind of data. In this sense, what I just talked up to now is actually the raw data, which are this first box, which represent the production of the dark matter distribution underlying, and then on which we build the maps and extracted the angular power spectrum, which are the ones represented in a previous slide. So we have at this point two possibilities. Either we go for a Fisher forecast approach, which is the main method or approach used in literature, or we do a step forward also in this sense, by implementing some likelihood estimation for doing parameter estimation in this kind of sense. And this is what we chose to do. And so, as you can see, we are missing some ingredients still to do this. In particular, we're missing the covariance matrix and the theoretical angular power spectra to compare with and then eventually do the likelihood estimation. So just I won't go deep into this slide, just to give you a brief idea what's actually the theoretical part underneath it, but you have on the first line, you have the theoretical expression, and then you have that, so you have to need to take into account for the window function, which take into account for the different redshift ranges and bin you are considering, and for the matter power spectra, from which then you can build the covariance matrix, and at last you can eventually evaluate the likelihood of the whole system of whole spectra. So this is what we're up to. So we chose to go for this road. And so you can see the only thing missing eventually is the MCMC sampler, so which eventually enables us to actually then get to the corner plots. However, we are not able yet, I'm not able to show you yet the plots because the analysis is still ongoing, but I can show you some steps we are willing to take in the future and eventually to discuss further. So the first step will be actually to plot and actually find this analysis, finish the analysis, so eventually to compare all this analysis to the state-of-the-art current situation, which is the one to go beyond so the one with the Fisher matrix forecast, so go beyond this kind of approach. And once this is set and actually evaluated, we will be able eventually to test for parametric and non-parametric cosmological analysis with lambda CDM and dark energy models, for which I refer to my colleague's work, Andrea Kotsumbo, who will be talking tomorrow. And lastly, we will be able to eventually to release publicly this likelihood in order to actually make it possible for everyone and to choose and to redo the analysis whatever he or she wants, in particular by enabling also the possibility to do a custom selection of which method to follow, which, for example, which tracer you want to use to do cross-correlation. For example, in my analysis right now, we're just taking into account for hydrogen and gravitational waves. And eventually, but however, in the future, there is open the possibility to also like add different traces. And lastly, we can also like to look for these synergies and eventually do proper forecasts for upcoming observatories. We can also like be able to select detectors, take into account the different sensibilities of each detector we are including in analysis. And so we are eventually really will be able to do this kind of forecast. And with that, I thank you for your attention, and I will be happy to take any questions.
Hi, thanks for a really interesting talk. I'm curious about the covariance matrix.
Yes.
How does it look?
Very bad. No, I don't have actually a plot or like a slide in which I have like printed up. The real problem here with this covariance matrix is actually, let's say, more or less the bottleneck of all this process is given by the fact that you have to take into account any combination. I don't know if you are able to see it from up there, up above, but you have to take into account for any combination of any traces and any redshift bin you are taking. So as soon as you scale up, let's say, your matrix is gonna be huge, especially because then it's not just a matrix of traces and redshift bin, but each element of the covariance is actually taking into account also each monopole we are considering. So in this analysis, I can show, which I'm doing here, we are actually just for like, take it like fast and easy for now, like to do it up to, let's say, not lower, like up to, let's say, 100 of as monopole scale. However, once eventually it will be possible, all this, let's say, all this framework is up and running, we would eventually also be able to run it up to, I don't know, let's say scale 400 or like, I don't know, 2000 to have some comparable. However, really at this point, it makes also not really sense to go at higher monopoles since, as you might see here, these are actually, for example, for the hydrogen map on the top, is actually really taking into consideration which are the sensitivity or the resolution of the telescopes or the observatory will have able to observe. And so going at deeper scales, we are not really, or like to smaller scales, we're not really able to resolve that. So it makes, for now, not real sense going like investigating higher scales. But at some point, for sure, in the future, it will be interesting to also discover and like have some work done in that direction. Yes.
Cool. Thanks very much.
Yeah.
Other questions?
Hi, nice talk. Can you give me an idea of how many GW sources would we need to get like a sufficient cross-correlation signal?
Also, in that case, very, very too much. Or like, let's say these simulations are done with assuming to have 10 to the 6 gravitational waves events from up to on all the redshift ranges. So we have, let's say, from, sorry, I have here. Like here, from here to here, you have in total, if you sum up, 10 to the 6 events. So I think in the like most abundant redshifts, so like let's say redshift 1, 1.5, in each, I think in each you have, if I remember correctly, like 10 to the 4th, 10 to the 5 events. While in the like other ranges, like for example, redshift 5, you have way less events because you have in this distribution, sorry, it's normalized, but you have this kind of distribution, and you can see that at redshift, a very low redshift, you have way less events than actually on the peak of the distribution. So let's say this simulation are done with 10 to the 6 events in total, but yes, and still we are, let's say Einstein Telescope will be able to look at these scales, but like on the whole lifespan, so it's gonna be challenging for sure.
Yeah, thank you.
Any other questions?
From this form of likelihood which you showed, it looks like you assume that covariance matrix doesn't depend on cosmological parameters which you estimate, right?
Yes.
So it means that covariance is dominated by noise terms, or?
Yes, we have you have some, the key point in cross-correlation is that any noise source from the signal kind of cancel out. So you have some noise given by the fact that you have some fluctuations in the spectra or in the density distribution you're looking at, but you have some other like systematics are cancelled out by using this cross-combining the two different, the tracer difference. So you have like anything which is related to the single outside, let's say, of the fluctuation of the density field is actually more or less systematically cancelled out by the cross-correlation.
But you assume that covariance matrix doesn't depend on parameters, right, which you estimate?
No, for now, it depends just on actually on the parameters which go into in the spectra. So you have some cosmological parameters because, of course, that's where you're looking at. You want actually to look at these dependencies, and unless that, you have sorry, I have really some issues. Okay. You have that these window functions, as you can see here, takes into account some astrophysical parameters given, for example, the number densities, but unless other size, or for example, otherwise there is no really astrophysical dependence on that. If I got your question right, sorry, I was not really able to hear correctly what you were asking for.
Well, in principle, covariance matrix should depend on cosmological parameters.
Yes.
When you do sampling, right?
Yeah, it does. But at this point, that's why we are running also Monte Carlo Markov chains. So we are actually able, eventually, we are taking any parameters that goes into the observation or like our simulated data go also into the theoretical ones. So we can really like play with any cosmological dependence in the system or like in the framework, let's say.
Okay, let's thank Matteo.